Welcome to lesson 6.1, titled Riemann sums. And everything we've seen to this point in this calculus course has been about what's known as differential calculus, working with derivatives, tangent lines, slopes, rates of change. And what we're going to move into now is what is known as integral calculus, which is really just the other side of that, more or less the inverse of what we've learned to this point. So let's start off with an example. A car travels at a constant 60 miles per hour, and we want to know how far does this travel in 6 hours. And that's not a very tricky problem on its own. If we think of the old distance equals rate times time, our distance would equal our 60 miles per hour times those 6 hours, and we would get a distance of 360 miles. Let's look at this one more way and say that for this car, we can model its velocity at any time as being a constant 60. And I'll be able to graph that over here, where on our vertical axis we will have velocity given in miles per hour, and on our horizontal we will have t in hours. And if we go back to thinking about the overall problem, where we're looking is right here at 6 hours. That's our cutoff. That's when we want to stop this and get our final answer. And what I want you to notice is the area blocked off by two things. Our v of t function, this horizontal red line up here, and this mark I've put in at 6 hours. Notice that if we just treat that as one big rectangle, the area of this rectangle would equal length times width, with a length being equal to 6, or in our case 6 hours, and a width or a height being equal to 60 miles per hour. And the overall area would equal 60 times 6, or 360 miles. This 360 miles that we got on the left is the same as the area bounded by our v of t function between t equals 0 and t equals 6. And that's the big connection that we're going to work on building as we move forward in the study of what I'm calling integral calculus, which is that the area under any curve represents a change in some quantity. In our case, looking at a curve that represented miles per hour, we got an overall change in the number of miles for this car that was in motion. And in fact, if we have a graph of anything representing a rate of change, the area under that curve will represent the overall change in our original quantity. So let's go ahead and change the problem up a little bit. Now we still have a car traveling for 6 hours, but this time its velocity, we're just going to be told, is a continuous function, and we record that velocity every hour as shown in this table right here. And same question as we had above. Approximately how far does this car travel in 6 hours? Well, you can see that was a really straightforward problem when we knew the velocity was constant, but now it's changing. Now we know at 0, we have 20 miles per hour, 1 we have 30, and so on as we move across this function. You can see the velocity moving up and down every hour. And the other issue with this problem is we have no clue what's going on in between. So how do we draw this function? The best we can do is guess the most likely velocity over any time interval. And then we can think about it like we did up top. If I can estimate a velocity between 0 and 1 hours, I can just multiply that by the 1 hour and get roughly the overall change in the number of miles. But the big question is, what is the most likely velocity for each of these smaller time intervals? So let's think of some way we can approximate that. And there's 4 ways that we're going to try. The first is, let's just imagine that the velocity at the start of every time interval is the closest to the overall velocity for that time interval. So what I mean for that is, I'm going to make a little table to kind of organize myself down here, and we're going to split this up into all these time intervals as shown on the graph, all the way up to 4 to 5 and 5 to 6. And what I'm going to say is, for this first part, from 0 to 1, let's use a velocity of 20, the one on the left side, and assume the car is at 20 miles per hour most of that first hour. From 1 to 2, we'll use 30, 2 to 3, 65, and so on as we go across. 4 to 5 will be 50, and from 5 to 6, we'll say it's 55 for the majority of that interval. And so if I wanted to approximate the total distance traveled by this car, I would think for my first hour that I would have 1 hour times 20 miles per hour. Just like we saw with the 60 mile per hour car at the top of the notes, we're just going to break this into 6 smaller problems. And I'm going to go ahead and add that to my 1 hour times the 30 for hour number 2. And I'll start cutting up the units here just to make this a little bit faster to write. I have 1 hour times 65 plus 1 hour times 75 plus 1 hour times 50 and 1 times 55. And putting this together, we will get approximately 295 miles, which based on the velocities fluctuating all the way across, 295 does not sound unreasonable if you think about putting yourself in as the driver of this car. And one thing I'll do really quickly before we move on is make a reminder of which function values we used in this first approximation. So for our time interval from 0 to 1, we used the velocity on the left at 0. 1 to 2, we used velocity at 1, and so on, only using the velocity recorded at the first time value. So another way we might think to do this is to use the velocity right in the middle of the interval. So like on the interval from 0 to 1, what if we just got the velocity at 0.5 hours or at 30 minutes and used that? On the interval 1 to 2, we'd use 1.5, and so on. Well, what I'm hoping is you realize the issue with thinking in this way. And the issue is going to be our data that we have only reports velocities at every hour. It doesn't report them in the middle. So we don't have enough info to do this. And in the future, we'll see problems where we can, and those ones might give us better approximations, but for this particular problem, we're going to be limited by the data that's reported to us. So let's try one that we can do. Let's use the velocities at the right end of each interval, so kind of the opposite of what we led off with the left end. So thinking about from 0 to 1, instead of using that 20 miles per hour at time 0, let's imagine that the velocity over that first hour tends to be closer to that 30 miles per hour that we report at t equals 1. On the second interval from 1 to 2, we'll use the velocity at 2, and so on. V at 4 for the hour from 3 to 4, V at 5, and V of 6. And notice, we'll see a lot of repeat values from that very first table. The 20 is going to be gone because we've shifted everything over by 1 hour. So a V of 4 of 50, V of 5 of 55, and taking a peek back up to our table at the top, using V of 6 as being 40 miles per hour. And so this one we will be able to make an approximation. Over the time interval from 0 to 1, that's 1 hour, and over that 1 hour, we're going to approximate that we are going 30 miles per hour, plus our 1 hour times 65, and so on. And you might think putting in this 1 hour is kind of unnecessary, and for this problem, especially with all the multiplication, it is. But in future problems where we change these intervals, and they're anything other than 1, it's going to be important for us to make sure that we are writing out all of our work and being able to see all these computations. And adding this all up will give us an approximate distance traveled of 315 miles. And the last way we'll look to approximate, and maybe something you would have thought of at the beginning, will be to average the velocities at both the left and right ends. And thinking about how we would do an average, that would mean on the interval from 0 to 1, we're going to take v of 0 plus v of 1 and divide it by 2. Second interval, we'll take v of 1 plus v of 2 and divide that by 2. And we'll keep going with this calculation all the way across. And really, especially with only averaging 2 values out, this just means we're taking the velocity right in the middle of the velocities at the ends. And just make sure we're not getting this confused with what we said in the second type of approximation. We're not using the middle time value, we're using the middle velocity. And since we know velocities at all these times, these are numbers that we will be able to evaluate. So the average between 20 and 30, what's happening at 0 and 1, would be 25. From 1 to 2, we'll have an average of 47.5. 2 to 3, an average of 70. 62.5 here. 52.5 from 4 to 5. And from 5 to 6, 47.5. And we can go ahead and set up our calculation to approximate the distance traveled using this last technique. And after we're done with this one, that'll kind of take care of every possible combination we could think to do with these various numbers. We are very limited by what we can do based on the data presented to us. And for this one, adding up all of those average velocities will give us an approximate distance traveled of 305 miles. And if you're clever about it, you can think about what we've already done. This would have been the same as taking the average of our approximation using the left values and our approximation using the right values. And so visually, what are we doing? I want us to get back to the idea I started with, which was calculating a change as an area under a curve. And so what we've been looking at throughout this is velocity. And think about the area under any velocity curve as being a change in position. In our case, it was a change in miles. But this can be applied to any function. And so let's say we have this curve over here, f of x. Or as an example, you can think of it as being v of t. This curve could be doing anything between any 2 points. In our case, we're calling those 2 points a and b. It could increase, it could decrease. And unless we're given an actual function, we don't know what it's doing, like we saw with the problem with our velocity table. So approximating this area is going to be very tough. That is not a shape that we know. When we started on this set of notes, the area was very simple. It was the area of a rectangle. But this shape is very irregular. So what we do in order to solve this problem is let's turn this area into smaller shapes that we can calculate the area for. So where we'll start, let's look at our right approximation like we talked about with our velocity table in the previous big example. And what we were really looking at when we did that right approximation was taking this entire interval of time, of x values, whatever it might be, and splitting it into smaller intervals. And saying that we were going to use our function value at the right side of any interval to approximate, in our case, our overall distance traveled. Well, if you think about it, in the example, we were doing time, interval, times velocity at the right end of the interval. Multiplying those two dimensions, that's just the area of a rectangle. And the rectangles we're finding the areas for would look like this. Rectangles that have a certain width and whose height is determined by the function value on the right. And I can go across and think about all those different rectangles that we were using to make our approximation. And notice as we go through this, some of the rectangles go too high. They go above the curve and they add extra area that we don't want. And some of them stay below. All really depends on whether our function is increasing or decreasing. And what you hope is the parts of the area that are over the curve kind of balance out with the parts underneath to give us a close enough approximation. It also helps if we ideally have as many rectangles as possible, or as many intervals as possible. And so if you go back, the name I'm going to give this approximation now is a right rectangular approximation. And imagining cutting up this area into rectangles whose height comes from the right side of every interval. And the overall area under f of x from a to b on that x-axis will equal, there's our sigma to show sum of each interval width times the function value at the right side of the interval. And so let's contrast this with a left rectangular approximation. Again, saying we have this irregular area underneath this curve, we'll go ahead and split it into smaller intervals, but how we're going to do this one is I'm going to create rectangles whose heights all come from the left side of each interval. So this first rectangle will actually have a height over here at A, whatever distance that is from the x-axis up to the curve. Every interval that we've set up, our rectangle's height is determined by the left side. Notice how these first several are underneath this particular curve because it's increasing, and then they start getting a little bit higher. And then we start getting some over approximations that again we hope kind of balance everything out. And how we would figure out this area under f of x from a to b, the sum of the interval width times the function value at the left side, at the left end of the interval. The next one we're going to approximate using the midpoint. And this was one we had attempted to look at with our first example, but we couldn't because of incomplete data. So how this would look, again, splitting up our overall problem into smaller intervals, instead of using the left value for the interval or the right value, what we'll look at instead is picking a point halfway, if we have enough information to do it, and making our rectangle, making its height the function value at the midpoint for the interval. Again, this is only going to work if we could actually figure out the function value at those midpoints. And notice how for these rectangles, it certainly appears that if any part of the rectangle is above the curve, there's also a corresponding part that's below. And it does seem like with the midpoint, those are going to balance out a lot better than they did with the left and right. So if we have the information, this midpoint approximation is going to give just a slightly better final result for that area. And how we would work with this one is the area under f of x from a to b for our midpoint approximation will be the sum. Notice we're still going to have the width of our rectangles be the entire interval width, but the height will be determined by the function value at the midpoint of the interval. And finally, we're going to have what we're going to call the trapezoidal approximation. And this is going to be the same as what we saw with our velocity example when we did the average of the left and the right. What I want you to think about for this one is think about what the area of a trapezoid is. It's 1/2 the height of your trapezoid times the sum of the two bases, the two sides of any trapezoid that are parallel to each other. And when you look at this formula, notice that this 1/2 and the sum of the bases, that represents an average, adding two things and dividing by 2. And so visually what we'll see, we think about function values at the ends of those intervals, but now instead of making rectangles, we're going to be actually creating a different shape. We're going to be closing off our shape by connecting the function values at the top of the left side and the top of the right side and creating trapezoids. And notice how even if they end up under the curve, the trapezoids don't tend to leave very much open space. And especially for one like this, it looks like if I could get the areas for all these trapezoids, I would actually have a very accurate approximation for the area under the curve. And in fact, the trapezoidal approximation will always be the most accurate, the most realistic to whatever application we're doing. And so in order to do this one, we're still looking at the area under our function from a to b. What we'll have is the sum of the interval width, that will really represent the height of our trapezoid times the average of the left and right function values, which will represent our 1/2 b1 plus b2, 1/2 the sum of the bases. And so the example we've looked at, these various visuals that we are investigating here, all these ways that we're looking to approximate the area under a curve, to approximate the change in a quantity, bring us to the big term for this lesson, Riemann sums. And the idea behind a Riemann sum is that we split the area under a curve into smaller geometric shapes with known areas, and we add those areas to approximate the area under a curve. So in our case, we were splitting into rectangles to approximate that area, splitting into trapezoids, but all shapes that had known area formulas in order to make those calculations easier. And between this lesson and the next two, we'll go a little bit more in depth on this process, get a chance to better investigate why we're doing it, and see overall what we are building to with this discussion of what we're calling integral calculus. So that'll do it for lesson 6.1. Please make sure to review and summarize these notes, be comfortable with how to do all 4 of these approximations that we've investigated, and when you're ready, move on to the practice. Thank you for watching.